Good morning, dear friends. We are going to face the October monthly test now. And for this monthly test, you have this lesson also included, that is Unit 3, Periodic Classification of Elements, under which previously we studied the Dobrynin's law of tires and Newland's law of actives, Mendeleev's periodic table, and Moseley's modern periodic table. Now we are going to see periodic trends, atomic radius, effective nuclear charge, ionic radius, and Paulink's method to find out the ionic radius. Okay, this is in unit. This is in unit 3, periodic classification. Okay, so take your book, and in your book it is given in page number 68. Okay. Now, periodic trends in properties. As we discussed earlier, the electronic configuration of the element shows a periodic variation with increase in atomic number. Similarly, a periodic trend is observed in physical and chemical behavior of elements. In this section, we will study the periodic trends in the following properties of elements: atomic radius, ionic radius, ionization enthalpy, electron gain enthalpy, or that is called as electron affinity and electronegativity. The first one is atomic radius. Okay. Atomic radius of an atom is defined as the distance between the center of its nucleus and the outermost shell containing the valence electrons. It is not possible to measure the radius of an isolated atom directly except for noble gases. Usually, atomic radius is referred to as covalent radius or metallic radius depending upon the nature of the bonding between them. Between the concerned atoms. Okay, now one example is given here. It is 1/2 of the internuclear distance between two identical atoms. Identical means the same atoms linked together by a single covalent bond. Internuclear distance can be determined using X-ray diffraction studies. For example, the experimental internuclear distance in chlorine molecule is 1.98 angstrom. Its covalent radius of chlorine is calculated Cl bond Cl, which is equal to radius of chlorine plus radius of chlorine. So Cl bond Cl is equal to 2 RCl, that is 2 radius. Therefore, radius of chlorine is equal to distance between Cl and Cl, Cl bond Cl divided by 2, that is 1.98 by 2, which is equal to 0.99 angstrom. Next is covalent radius of chlorine is the 99 picometer. PM means picometer. The formation of covalent bond involves the overlapping of atomic orbital and it reduces the expected internuclear distance. Therefore, covalent radius is always shorter than the actual atomic radius. The covalent radius is individual atom. An individual atom can also be calculated by using the internuclear distance of different molecules like A and B between two different atoms A and B. The simplest method proposed by Schumacher and Stevenson is as follows. That is, distance between A and B is equal to radius of A plus radius of B minus 0.09 XA and XB. Here XA and XB are the electronegativities of A and B respectively. Now let us calculate the covalent radius of hydrogen using the experimental distance HCl. Value is 1.28 angstrom and the covalent radius of chlorine is 0.99 angstrom. In Pauling scale, the electronegativity of chlorine and hydrogen are 3 and 2.1 respectively. So the distance between H and Cl is radius of hydrogen plus radius of chlorine minus 0.09 XCl and XH. Here, if you are substituting those values, you will get 1.28 is equal to RH plus 0.09 minus 0.09 into 3 minus 2.1. Those are all the electronegativities of chlorine and hydrogen, which is given in the data. And now we will get 1.28 is equal to RH plus 0.09 minus 0.09 into 0.9. So I will get 0.081. If you are subtracting that one, you will get 0.909. So the RH value is 1.28 minus 0.909, which is equal to 0.317 angstrom. Next is metallic radius. Metallic radius is defined as 1/2 of the distance between two adjacent metals, because in metals they are very closely packed. For example, the distance between the adjacent carbon atom in solid copper is 2.56 angstrom, and therefore the metallic radius of copper is 2.56 divided by 2, which is equal to 1.28 angstrom. The metallic radius can be calculated using the unit cell length of metallic crystal. You will study those things in detail in the lesson solid state. Next is periodic trends in atomic radius. Variation in period. Atomic radius tends to decrease in a period as we move from left to right along a period, and the valence electron are added to the same shell. The simultaneous addition of protons to the nucleus increases, and the nuclear charge as well as the electrostatic attractive force between the valence electrons and the nucleus. Therefore, atomic radius decreases along the period. Effective nuclear charge. In addition to the electrostatic forces of attraction between the nucleus and the electrons, there exists a repulsive force among the electrons. The repulsive force between the inner shell electrons and the valence electrons leads to a decrease in the electrostatic attractive forces acting on the valence electron by the nucleus. Thus, the inner shell electrons act as a shield between the nucleus and the valence electron, and this effect is called as shielding effect. The net nuclear charge experienced by the valence electron in the outermost shell is called the effective nuclear charge. It is approximated by the equation ZF is equal to Z minus S. Here, Z is the atomic number and S is the screening constant, which can be calculated by the Slater rule, and the Slater rule is given here in step 1. First, we should write the electronic configuration of the atom, and you should rearrange it by grouping as ns and np orbitals together and others separately in the following form. That is, we have to, after writing the electronic configuration, we have to group them like 1s one group, 2s and 2p together one group, 3s 3p one group, 3d alone one group, 4s 4p one group, 4d one group, 4f one group, and 5s 5p one group. Like that we have to arrange. That is the first step. Second step, identify the group in which the electron of interest is present. The electron present right to this group does not contribute to the shielding effect. Each of the electron within the identified group, that is denoted by N, shields to an extent of 0.35 unit of the nuclear charge. However, it is 0.3 unit for 1s electron, that is for only hydrogen and helium. Shielding of inner electron. Third step is shielding of inner electrons. If the electron of interest belongs to either s or p orbital, each electron within the n- group shields to an extent of 0.85 unit of nuclear charge, and each electron within the n-2 group or even lesser group, that is n-2, n-3, n-4, like that, they completely shield, that is to an extent of 1.00 unit of the nuclear charge. If the electron of interest belongs to d or f orbital, then each of the electron left to the group of the electron of interest shields to an extent of 1 unit of the nuclear charge. Next step, summation of the shielding effect, and you have to sum up all those shielding effect of all the electrons that gives you the shielding effect. For example, let us take the calculation of effective nuclear charge on 4s electron and 3d electron in scandium. The electronic configuration of scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d1. Next, we have to rearrange those things. That is 1s, one group, 1s2, 2s, 2p8, another one group, 3s, 3p8, another group, 3d1, one group, and 4s2, one group. 4s2 group is called as nth group. And coming to the tabular column, n is 1 and its effect is 0.35. So if you are multiplying 1 into 35, you will get the same 0.35. n minus 1 electrons are 9. That should be multiplied by 0.85. The answer is 7.65. And n minus 2 and others, total electrons are 10 electrons. That should be multiplied by 1. So you will get the answer 10. If you are summing of all those effective charges, then you will get 18. So now coming to the formula, ZF is equal to Z minus S. That is 21 minus 18, which is equal to 3. Then calculation of the effective nuclear charge on 3d electrons. Again the same thing. Again you have to grouping it 1s2, 2s2 p8, 3s 3p8, 3d1, 4s2. And here 4s2 is the beyond the electron of interest. So we are not calculating that one as S. We are considering the 3d as N. Okay. So group N, only 0 electrons are there because the one electron we are going to calculate, there is no remaining electron in it. So it should be multiplied by 3, 5 means you will get the same 3, 0. N minus 1 and others is 18 electron. That should be multiplied by 1. So we will get the answer 18. So the S value is 18. And substituting that one in the formula, ZF is equal to Z minus S. You will get 21 minus 18. The answer is 8. Like the same, here shielding effect from inner shell electrons using the Slater rule. N is equal to N, the Ns electron is multiplied by 0.35 and for 1s electron alone it is 0.3. And N minus 1 it is multiplied by 0.85 and N minus 2 and others it should be multiplied by 1.00. And here some of those in this tabular column, the atomic radius, that is the covalent radius of the second period elements are given here. Lithium, beryllium, carbon, nitrogen, oxygen, fluorine and neon. And those covalent radius are given here. 167 for lithium, beryllium 112 and carbon 87, nitrogen 67, oxygen 56, fluorine 48 and neon 38. Then one more problem is given here using the Slater rule, and in this one calculate the effective nuclear charge on a 3p electron in aluminum and chlorine. And you have to substitute the values of aluminum you have 13 and chlorine you have 17. First you should write the electronic configuration and find out for which electron you are going to find out the effective nuclear charge, that is a 3p electron. And next you have to put the values, substitute and find out the answer. If you have any doubt, you can ask in the clarification class. Next, variation in group. In the periodic table, the atomic radius of the elements increases down the group as we move down a group. New shells are opened to accommodate the newly added valence electrons. As a result, the distance between the center of the nucleus and the outermost shell containing the valence electrons increases. Hence, the atomic radius increases. The trend in the variation of the atomic radius of the alkali metals are given in this graph as well as the following tabular column. Lithium 1.34, sodium 1.54, potassium 1.98, rubidium 2.11 and cesium 2.25. And here one problem is given, and this problem you have to plot a graph for this one and find out here the second group elements, different groups elements or a covalent radius are given there, and you have to plot a graph and find out what is the difference in it, and you have to explain the reason also. Next is ionic radius. Ionic radius and atomic radius are more or less the same. In the place of atom, you are going to substitute ion. That is, it is defined as the distance from the center of the nucleus of the ion up to which it exerts its influence on the electron cloud of the ion. Ionic radius of univalent crystal can be calculated using the Paulink's method from the inter-ionic distance between the nuclei of the cation and the anion. Pauling assumed that the ions present in the crystal lattice are perfect spheres, so that they are in contact with each other. Therefore, the distance between the cation and the anion is equal to the radius of cation plus the radius of anion, that is Rc plus Ra minus. Here, D is the distance between the center of the nucleus of the cation and the anion, and Rc plus and Ra minus are the radius of cation and anion respectively. Pauling also assumed that the radius of the ion having the noble gas electronic configuration, that is Na plus and Cl minus configuration, are 1s2, 2s2 and 2p6 configuration, which is the configuration of neon noble gas, which is inversely proportional to the effective nuclear charge. That is, Rc plus radius of cation is proportional to 1 by Zf C plus, and Ra minus radius of anion is equal to 1 by Zf A minus. Here Zf is the effective nuclear charge and Zf is equal to Z minus S. This only is studied earlier. So dividing those two equations, then you will get Rc plus by Ra minus is equal to Zf A minus divided by Zf C plus. On solving the equation 1 and 4, the values of Rc and Ra can be calculated. Now, using this method, we are going to calculate the Na plus and F minus in NaF crystal, that is sodium fluoride crystal, whose interionic distance is equal to 231 picometer. Distance. The distance of NaF is equal to Rna plus plus Rf minus. Therefore, this value is equal to 231 picometer, that is given in the problem. And we know that Rna plus and Rf is equal to Zf F minus by Zf Na plus. And Zf fluorine is Z minus S, which is equal to 9 minus 4.15, and you will get the answer 4.85. Like the same, Zf for Na plus is 11 minus 4.15, we will get the answer as 6.85. If you are substituting those values in that formula, that is Rna plus by Rf minus, we will get 4.85 divided by 6.85, and the value is 0.71. And Rna plus is 0.71 into Rf. Substituting this value in the previous equation, then you will get 0.71 Rf is plus Rf is equal to 231, and 1.71 Rf is equal to 231 pm. Therefore, Rf is equal to 231 divided by 1.71, which is equal to 135.1 pm. Substituting this value in Rf, we will get the value of Na plus is 95.9 picometer. Okay. Then the next is ionization energy, that is mentioned as IE. It is defined as the minimum amount of energy required to remove the most loosely bound electron from the valence shell of the isolated neutral gaseous atom in its ground state. It is expressed in kilojoules per mole or in electron volts, and the electron volts are abbreviated as EV. And for example, mg plus mg means it is in the gaseous state, plus IE, that is ionization enthalpy, gives m plus 1 electron. Here IE1 represents the first ionization energy. Next is successive ionization energies. The minimum amount of energy required to remove an electron from a unipositive cation is called second ionization energy, that is represented by the equation m plus IE2 gives M2 plus and 1 electron. In this way, we can define the successive ionization energies such as third, fourth, etc. The total number of electrons are less in the cation than the neutral atom, while the nuclear charge remains the same. Therefore, the effective nuclear charge of the cation is higher than the corresponding neutral atom. Thus, the successive ionization energies always increase in the following order. That is, IE1 is greater than IE2, is greater than IE3, like that. Next is periodic trends. The ionization energy usually increases along the period with a few exceptions. As discussed earlier, when we move from left to right along the period, the valence electrons added to the same shell. At the same time, protons are added to the nucleus. This successive increase in the nuclear charge increases the electrostatic force of attraction on the valence electron, and more energy is required to remove the electron from the valence shell. Thus results the high ionization energy. Let us consider the variation in the ionization energy of the second period elements. The plot of atomic number versus ionization energy is given here in this graph. In the following graph, there are two deviations in the terms of ionization energy. It is expected that boron has higher ionization energy than beryllium, since it has the higher nuclear charge. However, the actual ionization energies of beryllium and boron are 899 and 800 kilojoules per mole, respectively, contrary to the expectation. It is due to the fact that beryllium with completely filled 2s orbital, because beryllium number, atomic number is 4 and its configuration is 1s2, 2s2. So 2s2 is the completely filled one. So it is more stable than the partially filled valence electron configuration, that is boron. Boron atomic number is 5 and its configuration is 1s2, 2s2, 2p1. The electronic configuration of beryllium is 1s2 and 2s2, and that of boron is 1s2, 2s2 and 2p1. Similarly, nitrogen, whose number is 7, its electronic configuration is 1s2, 2s2 and 2p3. The electronic configuration has higher ionization energy, that is 1402 kilojoules per mole, than the oxygen, that is 1314 kilojoules per mole. Since the half-filled electronic configuration is more stable, it requires higher energy to remove an electron from 2p orbital of nitrogen, whereas the removal of one 2p electron from oxygen leads to a stable half-filled configuration. So, nitrogen needs more energy compared to oxygen. This makes comparatively easier to remove 2p electron from oxygen. Periodic trends in group. The ionization energy, while we are coming down, it decreases. As we move down a group, the valence electron occupies new shells. The distance between the nucleus and the valence electron increases. So the nuclear force of attraction on the valence electron decreases, and hence the ionization energy also decreases down the group. Ionization energy and shielding effect. As we move down a group, the number of inner shell electron increases, which in turn increases the repulsive force exerted by them on the valence electrons. That is, the increased shield effect caused by the inner electrons decreases the attractive force acting on the valence electron by the nucleus. Therefore, the ionization energy decreases. Now, let us consider this trend by considering the ionization energy of alkali metals. That is, the first group, lithium, sodium, potassium, rubidium, and cesium. Its graph is given here. Okay. Next is the first ionization energy of, that is IE1, and the second ionization energies are given here. For the elements names are not given, it is given as X, Y, Z, and from this data so you can find out which is having the most reactive element and which is having the least reactive element and which is the noble one. Okay. Next, electron affinity. This electron affinity we will see in our next class. And now I am going to conclude up to this. The remaining we will see in our next class. Okay. And now we are going to see the next we are going to see I give the question answer in the PDF form as a assignment here. You should see that one and you should copy that one in your notebook. Okay. And the remaining we will see in our next class. Is it clear? Okay, ma. Thank you very much. Okay, ma. Thank you very much for everything. And we will meet and read all those questions for the coming October monthly test. And we will see in our next class. And any doubt, we can clarify with the class. Okay. Thank you.